probably better wording part of the international standard, or SI. K sub C. There are various different subscripts I will use for that. Sometimes I'll do K sub E. And that is a lowercase k. So this is the force onto from 1, so R1. All right, so let's parse this out a little bit. R is the distance between them. If they're point charges, then it's just straight up the distance between them. If you're dealing with multiple charges, it would be basically the center of charge. And there's some shortcuts that we can take when we get there. This idea of 2, is it really 2? Maybe it's 2.01, 2.00, 1.9999. There are some physicists who actually have gone through to try to figure that out. And the difference between 2 and the actual number, all they've figured out at this point, at least as of 1971, it's possible that they stopped at that point, the difference between 2 and the actual number is less than 2. I just saw it, 3 times 10 to the negative 16th. So, close enough to 2. Now I'll bring this up, one, the fact that, I guess the main reason I bring this up is just to show that a lot of the stuff that we're talking about here, there are physicists who do go in and try to figure out, all right, so is that really the number that we think it is? These are obviously the charges. I don't think we use Q for anything else in this course. And K, I'd actually use K sub E more often, is known as either Coulomb's constant or the electrostatic constant. Now there is another form of this that actually is very convenient later on. Right now I just like using K, but there is another form which some students prefer. Instead of writing K, they write this right here. And that is a 4 pi on the bottom. And then this epsilon sub 0, this is known as permittivity. The sub-zero of free space. It's approximately equal to 8.85 times 10 to the negative 12. That would be meter squared per Newton Coulomb squared. Whereas K, if I can write that better, K sub E is approximately equal to 8.99 times 10 to the 9th. Oop, that unit's off. This is Newton meters squared per Coulomb squared. This would be the reciprocal of that. So Newton meters, Coulomb squared per Newton meter squared. That's it. I apologize for that. Oftentimes for the electrostatic constant, I'll just use 9E9. The reason this is convenient is that, yeah, using 9 times 10 to the 9th works really well for the value of K, but when you start dealing with charges in the presence of other materials, then K doesn't change, but epsilon will. So if I have a plate filled with charge and another plate filled with charge. If there's nothing in between them, I can get away with this or that. But if I stick something in between these two plates of charge, then this equation actually becomes that. You drop the subscript because it's no longer free space, and we have a mechanism for dealing with it now, unlike this constant. But for right now, we're not worried about that. Just a teaser of what's coming up when we get to capacitors. So let's just do a quick plug and chug. I have a proton, another proton, and let's put them 2 meters apart. What is the magnitude of the electric force acting on them? Let's stick a little subscript E here. What is the magnitude of the gravitational force between them? All right, so the formula, we have the formula right over there. So 9 times 10 to the 9th. Times the charge of a proton, 1.6 times 10 to the negative 19th. Times, well, the same thing again. Divided by the distance between them squared. So first off, any questions on why those numbers are where they are? About what I did?
Which one? Which do each represent again? So the 9 to the 10, or 9?
Sorry,
9, what do each ones represent?
Oh, okay. So this is my case of E, or C. This is the charge of the proton of the first object, charge of the second one, it's also a proton, and this is the distance between them squared. Yes?
When does the R hat get involved?
All right, so R hat, first off, what does the hat represent?
That's a vector?
You said a vector?
Yeah, it's a vector.
More specific than that. I've been told in math class that the hat just represents another vector, but it's more specific in physics. You dealt with I hat, J hat before? What did I hat before I hat, J hat?
X and Y.
Been brainwashed. Someone who has not been brainwashed by the math people.
It's just like the Cartesian plane, or like it's that specific kind of plane?
Okay, typically, but the reason X and Y typically like this, I hat, J hat could be in whatever direction I feel like it, just as long as they're perpendicular. But when did you use I hat, J hat? They do come into effect in dot products and cross products too. But you should have been using them before you even got that far.
Just when you wanted to pick your own like coordinate system, or you pick your own.
In a sense, yeah. They indicate direction. So this right here, the unit vector, it's a unit vector. It is a vector, so it has a magnitude and a direction. What is the magnitude of a unit vector?
1.
All right, so the magnitude of 1, so the magnitude of our 1 hat is 1. And the direction, if you're dealing with I hat and J hat, the direction depends on what you decide. I say the I hat's that way and J hat's perpendicular to it in some convenient direction. K hat would be perpendicular to I and J. For R hat, we're dealing with a radial unit vector. So specifically, this is a radial unit vector. And a radial unit vector points away from the center, whatever you define the center to be. So radial unit vector points away from center. So I hat, J hat, you get to decide which direction those are pointing in, but radial vector, only decision you have is what is your reference point. In this case, my reference point is, is R sub 1 is charge 1. So if this is charge 1 and charge 2, the force at charge 2 is R1 hat. If I end up with a negative value, that means it's the opposite way, so it's being pulled towards it. If it's a positive value in front of this vector, it means it's away from your center. Is that sufficient?
Yep.
Okay. In this particular case, I just asked for the magnitude,
Yeah,
not the worry, so I wasn't gonna worry about direction.
okay.
Anyone that work this out? Would someone be kind enough to pull out a calculator? Because otherwise you would force me to do it in my head. What's the answer? What's the actual answer?
I got 5.76 times 10 to the negative 23.
How was I so far off? Anyone else get the same thing he got?
I got 5.76 e to the negative 29.
This is a 9, negative 19, negative 19. That,
Is it negative 19?
yeah, these are negative 19s.
Oh,
Oh,
okay.
you did negative 16s?
Yeah.
Yeah, I guess my sloppy handwriting just bit me there. All right. Units? For those who have not had me before, if you present an answer like that and just left it, I would take off 30%. Because units matter. If units don't matter, the answer is always 1. Because I could come up with units later.
Newtons,
Why?
because with the constant we have, the coulombs cancel out, and we just, oh, it's force.
Yeah, but either way, you can actually look at the units and start doing the canceling, or just think, oh, we're finding force.
Yeah.
All the units that we're using here are all standard international, so my answer better be in international standard. I guess I flipped back and forth by which word I put first. All right, the gravitational force. Anyone happen to remember what the formula for universal gravitation is? Ignoring direction. Magnitude. I'm gonna take that as a no. Colin, you look like you want to say something.
I can't remember, it's almost the exact same thing, it's a different constant, and instead of charges, it's mass.
There you go. Big G, mass 1, mass 2 over r squared. So the big G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of a proton. Now, hopefully I've got it written down here. Mass of a proton, 1.67 times 10 to the 27th. Sorry, I've said that wrong. 1 times 10 to the negative 27 kilograms. It's in kilograms. I got 2 protons, so I'm just squaring it. No, I'll write it out. Divided by r squared, or 4.
5.65, 10 to the negative 65.
65 units.
Still newtons, cause it's still force.
Say it again?
Still newtons, cause it's still force.
Absolutely. Notice the huge contrast. Now, these aren't particularly large forces because we're only dealing with a single proton. Later on, we'll be dealing with a whole mass of protons, or a whole mass of charge, I should say. But considering the order of magnitude difference is more than 10 to the 30, this is our justification for why gravitational force, if we're dealing on this level right here, the gravitational force we can ignore. So when we do force diagrams, when we analyze situations to look at the forces, yeah, these are not significant. The only time that the gravitational force might come into play is if we have enough charge on an object, like in the lab that you're going to do on Thursday, enough charge on the object so that it actually will move something, and then we do have to take weight into account. But on the small level, it is insignificant. If you wish to take gravitational forces into account, then enjoy the asylum. It's a path to madness. All right, any questions at the moment? All right, I'm gonna do one more of the, oh, yes,
I'm
Faith.
sorry, what is the subscript on the first, equation?
That?
Yes, what is that?
That's an E for electric force. Other questions at the moment?
Are we gonna have to know the mass of proton?
You know, something like that, it's nice if you remember it, but something like that on a test or a quiz, you just look at the top of the first page, or the quiz, look at the top of the page, and it'll be there. The basic charge, there is, when it comes time to the chapter quizzes, there's a set of problems that will be assigned, and I'm gonna pick 2 of the problems, change the numbers, and that'll be what I call the homework quiz. Before that is the flash quiz. So at the beginning, if you go on the Blackboard, oh, we forgot to do that at the break. If you go on the Blackboard, under coursework and then the chapter, the very first thing, or either the first or second thing says flash quiz or flash information, flash knowledge, something along those lines. That is stuff that I expect you to be able to regurgitate quickly. If you are great at memorization, this is in your bailiwick. If you're horrible at memorization, then that part's gonna be a struggle for you. But, you know, you should at least know something. And so the first part of the quiz, when we have a quiz on a chapter, is the flash quiz. And that's timed 10 minutes, and 10 minutes, I pick it up if you're not done. Because you should be able to just go boom, 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 boom. And then the second part is, at this point, untimed. And it's just the 2 questions from the whole questions in the chapter. So that should give you some sense of that which I would really like you to memorize. Although, if you don't have it memorized when it comes time for the test, the information's gonna be given there. It's just hopefully to help you save a little bit of time. And it also stems from one semester, I think it was a 152 course, when I asked, what's the SI unit for charge? And I got blank, moving back at me. And I thought, no. There's some things people need to know. All right, so let's do one more. So I have an electron here, I have a proton here, and I have a proton here. The distance between the proton and the electron is 2 meters on the left and 2 meters on the right. The electric force on the electron. Notice I didn't put absolute value there. I am looking for a vector as an answer. I'll let you sort of come up with what you think the answer is. When you have an answer, just sort of give a nod or a wave, just so I know that you're there. And then we will take a look as a group. And there definitely are two approaches to this. So I'm picking roughly the same thing just because the math's already been done. Don't leave this part.
What's the subscript on the F, on the force?
The two subscripts, we have an E here for electric and then E for the electron. I want to know the total force acting on the electron.